This diagram tests relationships. The prompt establishes Tom Smith's wife is Mary Stone. Semantic nodes activate and a wire connects them. Follow-up, who is Mary Stone's husband? The model holds the exact same ingredients. Zero new information is required, yet performance plummets. It retains the entities, but drops the precise wiring assigning each to their slot. When a model fails here, the output isn't random nonsense. It stays annoyingly adjacent to truth. The system provides the right semantic neighborhood, but misplaces the exact target. Calling this a hallucination flattens the diagnosis. Hallucination implies a fabrication from thin air. Here, the evidence is entirely present. The system simply mismanaged the internal assembly. This precise failure is known as the binding gap. It is a discrete architectural breakdown where a model preserves the semantic material, but loses the exact attachment required when demanding role reversal. This diagnostic matrix maps exact boundaries. Quadrant 1 is a retrieval miss. Data never entered the context. Quadrant 2 is decomposition failure. It initiates the wrong subproblem. Quadrant 3 is generic hallucination, fabricating from scratch. Quadrant 4 isolates the binding gap. Semantic pieces are present, but specific wiring fails. Defining these boundaries proves generation and retrieval failures are distinct mechanical events, requiring separate diagnoses. By applying precise vocabulary, engineers stop treating wiring flaws as data quality problems. It clarifies exactly what needs repair. Moving past behavioral observation requires looking at the physical internal geometry of the transformer architecture. Binding is a tangible mathematical mechanism. Within this geometry, models utilize binding ID vectors. These are specific internal mechanisms that physically link entities to their attributes, rather than relying on a vague cloud of semantic association. Researchers have mapped a low-rank ordering subspace operating directly within this network. The orientation of this specific plane dictates which attribute belongs to which entity, acting as a mechanical steering wheel. Causal experiments verify this. Manipulating the direction of this specific subspace changes the model's pairing behavior instantly. The exact terminology we use to describe these vectors matters less than the physical reality they represent. The machinery exists. Because attachment is a localized function of the internal architecture, it is directly exposed to the model's physical and computational constraints. Attachment errors are therefore targeted mechanical breakdowns within the vector space, not random associative noise. This structural fragility scales up when we move from isolated entity pairs to the smallest natural language problem, thematic role assignment. Who did what to whom? Specific attention heads act as dedicated mechanisms for thematic role assignment, successfully extracting agent and patient information. The flaw lies in integration. While these signals are strong locally, they become diluted and weak as they integrate upward into the broader representational geometry. Research from Wang and Sun isolates two pressures causing this. The first is representational inconsistency. The model physically encodes the same entity differently depending on the role it currently occupies. The second pressure is conceptual entanglement. During the training phase, densely packed neighboring concepts actively interfere with one another. Learning and recombining these entangled representations naturally destabilizes those already weakly integrated role signals. This specific internal fragility provides the exact mechanical conditions necessary for a binding gap to appear. For enterprise applications, this weak integration is hazardous. It allows a model to produce grammatically flawless outputs, while masking unstable factual attachments underneath. To test this fragility under pressure, we examine a high-stakes professional application, evidence extraction for scientific meta-analysis. This text highlights the complexity of the task. The model must scan scientific prose and preserve strict, unyielding relationships between variables, statistical methods, and precise effect sizes across multiple academic papers. On single property queries, models spot these isolated atoms easily, but when scaling to multiple variable binding, extraction drops to near-zero reliability. The dominant error is cross-analysis binding drift. The model identifies a statistical method in one sentence, but physically carries it into the wrong comparison. we can immediately refute the explanation that the model simply failed to read the text. The logs confirm the variables and numbers are correctly recognized by the system. As structural density and numeric load scale, the model keeps enough semantic material to sound plausible, while the specific attachments required for analytical work fail. Traditional metrics for surface correctness and factual completion do not isolate a model's structural competence. Correct answers on generic benchmarks often mask underlying heuristic guesses. They reflect broad language modeling pressure, rather than proving the internal binding is stable and task-ready. This split-screen comparison illustrates a mandatory shift in evaluation engineering. We must put pressure on exact role assignment and structured extraction. Fixing this requires architectural interventions, implementing schema-aware records and JPA-based disentanglement to reorganize the internal wiring. If the binding gap is a true architectural bottleneck, we can make a precise predictive wager. Binding heavy tasks will consistently break long before open-ended summarization tasks fail. Role reversal and exact source attribution will always expose a model's weakness before generic explanations do. Progress in enterprise AI depends on the stability of internal attachments. Usable output requires that content remains bound in the specific form the task demands.